Welcome to BKW Physics. I'm Mr. McConley, and we're continuing our discussion on sound, and we're going to specifically talk about the Doppler shift today. But before I get into that, I want to expose you to this device here, which is a sound meter. And sound is a longitudinal wave made up of compressions and rarefactions, as we've already talked about. That's repetitive, but you can measure how loud something is in units of decibels. Now that's a whole other discussion how decibels work, because decibels is a relative scale. But anyway, and now that I've turned this on, my speaking, since I'm close to this, is registering as I talk as about 70 decibels at this distance. If I hold it further from myself, it's dropping down basically to 60. Now if we're all quiet in the room for a second, to you guys and to the video it sounds quiet. But there are ambient sounds. The heater unit's running, there's kind of like, general little shuffling and other sounds in the room. And when I just did that short experiment, we were actually measuring 52 decibels in this room. 52 decibels all the time in this room. Okay? So when you go to a concert or you go to a basketball game, it gets very loud, and someone says, oh, that's registering 100 decibels, or whatever the number might be, it's a little bit deceptive or a little bit confusing, because if you want to know how much is actually going into your ears, you would really need to hold the decibel meter right near your ear, because it vastly changes depending on where I point this. If I point it towards the sound, it'll register higher decibels. If I remove myself or back away from the sound, it'll also read different decibels. So we'll spend more time on another day talking about decibels, and I'll give you actually a relative, some benchmarks, like how loud is a siren on a fire truck. And I'll do that another day. For today though, the Doppler shift. If you've watched NASCAR in your life, you have heard the Doppler shift. The Doppler shift sounds something like this. A car is coming towards you like a NASCAR in a race. And then when it goes by you, it goes and then when they all go by, you know that sound from a race? I think you can relate to that if you've watched a NASCAR race or any sort of thing like that. You can also relate to that if you have heard an ambulance or something with a loud siren coming toward you. Did you hear the pitch changed? The frequency changed? That's the Doppler shift. So how do you show that? How do you draw that? It's fascinating, by the way, and it's going to lead us into a whole other group of things, applications of Doppler. And Doppler is a person's last name. So, if you have the source of sound here, whatever that sound is, that could be your race car, that could be your siren, that could be you yelling. And this source is moving this way fairly quickly. Now remember, back up before I even draw the rest of the picture. How fast does sound emanate through air? 331 meters per second, right. Now, just think of it this way. If sound, like, in three-dimensionally goes out 331 like this as I'm speaking, that's how fast it's going out. But I start moving really quickly this direction as I'm making a sound, now I'm starting to keep up a little bit. I'm starting to keep up with the sound. So the sound's moving 330, and if I'm moving 100, which I wouldn't be, but I could kind of start keeping up with the sound, so the picture is going to start looking like this. These lines I'm drawing represent wave fronts, or you can think of them as the crest of each wave. So the sound is traveling out in all directions at 331. However, since the source is also moving, these ones aren't escaping the source as quickly as these ones are. Does that make sense to you? These ones, they're still moving 331, but the source is kind of following them. It's like if someone's riding a motorcycle and you're kind of following them in your car, you're following the sound. All right, so just judging from how close the wave fronts are together here, what do you think the frequency is going to be? Is it going to be a high frequency or a low frequency?
High.
High. This is a high frequency. Now these, I'm not putting any numbers to it, I'm just kind of relatively speaking. That's a high frequency. And over here, you can see that it gets all stretched. This represents a low frequency. So when you hear that NASCAR sound again, ee-yo, ee-yo, high, low, that's because the sound, the car is going pretty quick. A NASCAR might be going 200 miles an hour, so the sound in front of the car is not escaping that quickly. It's like all crunched up in the front. Now this becomes, or it goes to an extreme when you're talking about a jet plane that can go Mach 1, which means what? It's going the speed, at least the speed of sound, right? So what happens is all of a sudden, if you think of the source as the jet plane's engine, all of a sudden the jet plane is moving so fast forward that the sound can't escape. In fact, it starts piling up in front of the plane, and then when you exceed the speed of sound, when you exceed 331 meters per second, which is like 760 something miles per hour, now you actually pass your own sound. And it makes a big boom, boom. Okay? That's Mach 1. And if you exceed it twice, you're at Mach 2. So if you're twice as fast as your sound, and the picture becomes very confusing to draw, because you got to think of how these waves, once you pass the waves, the picture gets really weird. Because you're the source of sound, but you've passed the waves that are coming out of, okay? You see how this gets confusing? So it's hard to draw, but the concept remains pretty clear for most people. Moving on to the next thing. There's an equation, like all good physics lessons, there's an equation that can help you find out how much the Doppler shift is, or basically it helps you find out how much the frequency is changing. And the equation goes like this. F prime equals F naught, velocity of the wave divided by the velocity of the wave plus or minus the velocity of the source. This is not an equation that will be on the Regents. It's not in your reference table. I'm giving it to you because it helps us understand the situation, and we can do some problems with this equation. So let me just define each of the things. First of all, the F naught is the original frequency of the sound. This is the frequency at the source. So this is the frequency at the source. This is the distorted or the changed frequency. We'll call it changed frequency. And it's changed because you're moving so quick. Okay? So if you're on the front side of this, it's going to be changed and it's going to be higher than normal frequency. If you're on the back side of this, it's going to be changed and it's going to be lower than normal. You see how that works? Where is the only spot that you might actually hear the same frequency as the source? Where would you be located if these two numbers were actually the same? Well, probably somewhere in this area. Just from the side view, you're probably going to get the correct, or the original frequency. Now, the velocity of the wave. In this case, we're talking about a sound wave, so we're talking about 331 meters per second at 0 degrees Celsius, which we'll talk more about because that speed actually changes when the air temperature changes. Every degree you go above 0, you add 0.6 meters per second to the speed of sound. Every degree you go below, you lose 0.6. And the velocity of the source is how fast, the thing that's making the sound, how fast is it traveling? Okay? Velocity of sound producer. Now the plus or minus is the only thing we have left that we got to talk about, because sometimes you got to use a plus and sometimes you got to use a minus. If the frequency is a smaller frequency, a lower frequency, like over here. In other words, if the thing is moving away from you, you're going to use the plus. If it's moving towards you, in other words, over here, like you have a high frequency, you're going to use the minus. Okay? And that allows you to figure out what the frequency of the source is compared to what it is once it's distorted because of the speed. Alright, one last thing here. What are the uses of Doppler? Because most of you have heard of Doppler radar. You turn on the Weather Channel and like, Doppler radar. Well, what happens with Doppler radar is you send a signal out. It's not a sound signal anymore, it's a different wave. But you send a signal out, and that signal goes and it runs into the storm, the snowstorm, the rainstorm, the clouds, whatever. And then it bounces back to the Doppler tower. And when it does that, the waves are either compressed or they're spread out. If the storm is moving away from you, then when the waves return, they're going to be all spread out. If the storm is moving towards you, then they're going to get compressed, and when they return, they're going to be shorter. And by using equations like this, you can say, oh, the storm is very dense and it's moving towards us at this speed. That's Doppler radar. Some other uses are, when you look out at the stars at night, they say that some of the stars are red-shifted and some of the stars are blue-shifted. And what that is, and it's actually visible. If you look at it, some of the stars have a slightly more red tint to them and some of them have a slightly more blue or violet tint to them. And that's based on whether that star is moving towards you or away from you. Because if it's moving towards you, then all the waves are going to be compressed. And if you look at your physics reference table, you will see that blue has a shorter wavelength. So if it's coming towards you, the wavelengths are going to be compressed. You're talking about, it's going to look bluish. If it's moving away from you, it's going to be red. Other uses of Doppler are for things like ultrasound. And that's very common now for anything from pregnancies to trying to look at an injury. They'll use ultrasound and they'll send waves in and then create an image based on how the waves are compressed or stretched out. And, oh, one other thing I should mention, radar. When we talk about Doppler radar, radar is actually an abbreviation that stands for radio detection and ranging. Most people don't know that, so it's kind of just a nice fact to end with. So for today, physics.